Hi, Wyatt. We missed you. So let's go with it here. Um, this thing needs to go up. Wants to go up and get it out of the way here. So, but let's go with it here. So just a quick review. Tell me which parts you need. We good? Just so you guys know. So this is the definition of L'Hopital's rule, right? By definition, it says that if you have two functions and they are technically ratios of each other, but it doesn't say that yet here. So if one goes to zero, the other goes to zero. That is called the indeterminate form. If one goes to infinity and the other one goes to infinity, that's called the indeterminate form. And if that's true, then what we can do is we can just take the derivative. That's it. We take the derivative, find the limit, and voila, we get to do that the fast way as opposed to the slow way from chapter 2. Okay, we're good there. Okay, you guys tell me which other pieces do we need to sort of see? Okay, cool. Let's do that. The product. So it's called the product form. So those are all definitions, and then we go here. There you go. Indeterminate products. Let's see. Okay, do we need this one real quick here?
Yes.
Okay, so it says if the limit goes to zero and one goes to infinity, notice it's a product between the two. Now the question is this: is this one going to zero faster than this one's getting bigger, right? And we talked about it just a little bit on Monday, right? Right before it was saying that if, let's say, I think we had the discussion here. So let's say this is one and this is one for convenience sake, right? And let's say this one's going to go faster. Let's say, right? So as something approaches A, whatever A is, right? Let's say this guy becomes 10 times smaller, so 1/10. This guy becomes 100 times bigger. So the product here is 1, right? What's the product here? 10. Notice, are we good there? So it's the product between, and then this one gets 100 times smaller. Now this one is 10,000 times smaller. Ooh, that's fun. Oh, 10,000 here. Boom. Yeah, now we're at 100, is that right? For the product between the two is 100. So it's really not a matter of which way is it going. It's really how fast is it getting there. That's kind of what you're trying to get at. Okay, are we good there? So the faster one wins. How do we show rate of change? It's derivatives. So the bigger a derivative is, that just means the bigger it's going towards that limit or faster towards that limit. Does that make sense to you guys? And then if we do this, this is a fun little thing. If we take one of these, doesn't matter which one you take, if you take the reciprocal and move it back into your denominator, it's L'Hopital's rule again. Because if g of x is going to infinity, 1 over infinity, 1 divided by 1 gajillion, kind of close to 0, is that right? So 1 over that number there, that is not gajillion, but right there, right? That becomes smaller and smaller, closer and closer to 0, right? So really it's L'Hopital's rule in disguise, that's all. If you flip the other one over, that means g of x going to infinity, but 1 over 0, or 1 over 0.000000001 becomes a huge number. So here's the other L'Hopital's form, which is infinity over infinity. So really, this is just an extension of L'Hopital's rule. Okay, are we good there? The products. Next, I think I did one example, and then we went to. Let me check. Nope, I'm in the wrong spot here. Let's see. There's a product rule. We did one example. We went to differences. There it is. There's that one then. Again, same thing applies here. If you have two things subtracting each other, right? The question is, which one goes faster? Now let's pretend this guy went faster, and we'll pretend the other way in just a bit here. Slower. And if you guys are just writing it down, go for it. So I have a function. You know what? Actually, let's put in functions into here. This would be actually a good one here to do. X squared minus x. If you did it on the graph, would that go higher and higher and higher forever? Yeah, because x squared is going up faster, right? Than x is subtracting it out. Good? If that makes sense. All right, so this one eventually is probably going to do something like this, right? It's going to go Actually, it's going to go probably from 0. But it's probably going to go like that eventually, right? Because why? X squared goes faster to infinity than x does. All right, let's switch it around. Let's say this guy was now the faster one. All right, so let's switch it around. This guy becomes x. This guy becomes x squared. Where are we going now? Yeah, instead of going up, now we're probably just gonna, it's probably gonna go like this, right? Bless you, bless you. Should we graph it? Just okay, just sort of see, just real quickly here. Let's see, where am I at? I'll go like this. Yeah. Desmos. Okay, so x to the power of 2 minus x. There it is. We're good. We went off to positive infinity eventually, right? Because x can't drag x squared back down. Changing it up again. Let's go the other way. Now we got this on our hands. All right, now the x squared is pulling it down, right? Okay, the weird one. You guys ready for the weird one here? How about if it is? You guys tell me what happens. Ooh, hold on, I'm not going to do that. Let's go back over here. What happens if this guy's 5x, this guy is 3x? What happens here now? Ooh, interesting. Are they going to balance each other out? No, they're not, huh? They are going to, technically it's 2x, right? So if you were to do them in a graph, you think, notice they're the same exponent, aren't they? Right? They're the same exponent. You think they're going to balance each other out, right? Because they're going, hey, I'm going to undo that one's work. But no, not really. Let me jump to here. All right, so it was what, 5x? Is that right? 5x minus 3x. Now it still goes up to infinity, right? Switch it around again. Oh, interesting. There it is. So actually, the constant itself could be actually be an issue here with this one. Okay, are we good though? It's just whoever's dragging which direction, right? Either up or down. Cool. Okay, and then the power. Yes, absolutely. All right, and then the power rule. There it is. We've got 3 different forms for powers. Yeah, this whole week, and it's supposed to get hotter and hotter this whole week, right? Hopefully this will not last. Hopefully it goes back down again. Okay, I see quite a few of you guys writing this down, so I'm going to pause here, let you guys write it down. So for indeterminate powers, and of course, oh, sorry, I misspelled it. Intermediate. No, it should be indeterminate. Let's take that off. Indeterminate powers. You just don't know which way the power is going to go this time. Okay, so the other little stuff, that's actually how you do the process here, but we're interested in just knowing the sequence here. So out of curiosity here, guys, talk to me here. Let's go this way here. Let's see. What happens if the 0 goes to 0 faster and the power is just dragging behind? What limit would that be? Let's see if this makes sense. So the base went to 0 a lot faster. It's going to be 0, isn't it? Everybody okay with 0? But the base goes to 0. Who cares what the power is, right? Could be 5 million still, right? But 5 million, 0 to the 5 million power is still 0, right? Because the base outwent. So in this case, it's going to be like this. It's going to be go to 0. How about this one? How about if this guy right here is a number still, and this one just went to zero so fast?
That's one.
Good, that's one, right? So notice there's a little power play here between the two here. Cool. Okay, so that's one direction. Now, does it have to be only 0 and 1? No. Based upon the, I'm saying, based upon the coefficients, based upon what functions is inside there, based upon how fast it's going, it could actually be a ratio. Good. But these are the two extremes. So good. Okay, let's go this one here. How about this guy goes to infinity? And this is not quite getting to zero yet. But this is getting huge. This is just bigger and bigger and bigger and bigger and bigger. Infinity. All right, the other way. This guy's a number, but then that goes to zero super fast. Back to one. Are we okay with back to one? All right, let's go the other way here now. So this one goes to one really fast. This one's kind of lagging behind. What's the answer here? One, that's right. One to any power is still one. Okay, and then this is just kind of a power getting to some number, but this just went off to infinity like crazy.
Nice.
Right, didn't quite get to one. We're still like, we're still 1.2, right? But we're taking it to the 5 millionth power. It's going to go off to infinity. We're good? So who cares if it's getting close to one, but the power is just so great.
What if it's like from this? What if it's like 0.95 and the power is smaller?
Oh, interesting. Yeah, that's right. So going the other way here, how about if it's under one, right? 0.9999, like that. But this is to the hugest power in the world. Where does that go? It goes to zero. Any numbers that are between 0 and 1, if you take bigger and bigger and bigger powers of them, will actually go to 0 because you're taking. That's true, yeah. Or basically it's a fraction and you're just taking bigger and bigger bits of a fraction. Okay, are we good there? That's cool. Good. Okay. Talk to me here. Do all three or concentrate on one of them? You guys talk to me. Should we do the product, make an example product, then do a difference, then do that one, and then we'll kind of go from there? Okay. And then we'll concentrate more efforts on, obviously, the powers, because those are the ones that kind of tend to mess up students here. Okay, so we got the forms. Let's jam with the problem. Here it is, limit. We did what? We did product first, right? Okay, let's go. Limit as x goes to 0 from the positive side of x, cotangent x. And tell me. That's that. And I'm going to go to so one product rule, one difference rule, and then we'll move on to one or two, based upon how we do on this one. How about that? Okay. So I see a product. Boom. I see this. But we got to think about what the graph looks like, right? At least have some kind of understanding. We're going to 0 from the right-hand side. So what is the limit off the side here? What is the limit as x goes to 0 from the positive side of x? It's 0. And if you look at a graph, we're looking at this right here. And we're looking for that piece right there, right? And as the limit is going to 0 from the right-hand side. So you can do it graphically wise as well. How about cotangent of x? We need to have a little graphic cotangent of x because we know the graphic cotangent of x. That is an easy one. We've memorized it. It's ingrained in our brain. Cotangent of x is, infinity, goes down, passes through pi over 2 right here. And then right at pi, there is a vertical asymptote. Absolutely. Yeah. All right, what is the limit as x goes to 0 from the right-hand side for cotangent of x? infinity. We good? It's this little piece right here as you're going to 0 from the right-hand side along the x value. The y value just shoots up like crazy. Okay, so do we have a form? Absolutely, we have a form. The form is 0 divided by, sorry, 0 multiplied by infinity. There's our form. Good. Let's apply L'Hopital's rule because L'Hopital rules applies. Or the extension of it, right? Okay, so here's a little trick now. We are going to make this into a ratio. Doesn't matter which one you choose, just make it into a ratio. So I'm thinking, cotangent. Is the cotangent the same thing as 1 over tangent? So I'm going to leave the x alone, and I'm going to put tangent on the bottom. Is that still the same thing? Oh, okay, we can do that. Technically, no, because cotangent is already 1 over tangent, right? So just snuck it in. Now notice before we even do this here, what's the limit as x goes to 0 from the positive side for x? 0. What's the value as x goes to 0, positive side of tangent of x? Let's check it out. Let's take a graph of tangent. Graph of tangent. There's a graph of tangent. This is L'Hopital's rule, right? This is the form of L'Hopital's rule of 0 over 0. That's it. So everything's eventually goes back to L'Hopital's rule. That's it. Okay. With that in mind, since L'Hopital rules apply, what shall we do? Take the derivative, absolutely. And we are almost done. Limit as x goes to 0 from the positive side of 1 over, anybody, derivative of tangent is?
Negative.
Is it negative secant squared or just secant squared?
Thank you.
Okay. Perfecto. I'm going to move my graphs around here or delete them. Just okay. Can we plug in the 0 into secant?
Yes.
What is the value of
1?
1? Okay. And 1 over 1 is 1. Crazy. Okay. So this is really crazy. You have a value in which something is going to 0, and the other one is something is going to infinity, right? And there's a ratio between those two, and the ratio technically is 1. They balance themselves out right at 1. Are we good? Okay, B. Let's go with B. Oh, you know what? I can actually get rid of that. Okay, let's see. That was the product rule. Should we do a subtraction? Well, of course we should. Limit as x goes to 0. I like the positive side of 0 here. 1 over x minus 1 over, e to the x. Give it a little bit of funness right over here. All right, give you guys a 30-second head start. Talk to the person next to you if you need to. Well, if you want to. And then you should talk to them right next. That's fine.
Mm-hmm.
Just joking,
Does
just
this work?
joking. All right, so let's see. I see a subtraction symbol here. So I'm looking for infinity minus infinity. So let's go with it here. So we got to think about this here first. What is the limit as x goes to 0 from the positive side of 1 over x?
Over 0.
1 over 0, 1 over 0.0000000000001, which is infinity, right? Cool. Okay, limit as x goes to 0. Oh, this might cause trouble for us here. Let's see. 1 over e to the x minus 1. Where does that go?
Anything 0 power is 1, so that's 3 plus 1.
So, yeah, anything to the 0 power is 1. So this becomes 1, but then 1 minus 1. Sure, we got some self-infinity happening. Cool. So do we have a form? Absolutely, we have a form. Form is infinity minus infinity form. Now, the question is this, which one is going faster, or is there a ratio that kind of sets up? All right. Guess what we got to do? We got to make it into a fraction. So I'm thinking like common denominators. I'm thinking stuff like that. Are we good? So let's see. What's my common denominator here? Yeah, x times e to the x minus 1. And then this one over here, same thing, x and e to the x minus 1. Those would be the common denominators. So then on top of the first fraction, I have myself. Yeah. E to the x minus 1, our multiplier, because it's 1 on top. And the second fraction has the x. Perfect. Putting it all together. The bottom I have as x e to the x minus 1. The top, let me go back real quick here. Oh boy. How about e to the x minus 1 minus x? Is that okay? I got e to the x minus 1 minus x. Ooh, okay. If you want to, you can verify now that we have as a ratio. You can verify that we have either 0 over 0, infinity over infinity as well, if you wanted to. But you know what? We verified that we had infinity minus infinity before, right? So it has to pull in through correctly. So the only other thing I would just change into this before taking a derivative, since I don't want to take a product rule. No, not a product rule. How about we just multiply through the x on the bottom? Then I don't have to take a product rule. It'll just be, oh, you know what? I still got to take a product rule. Shucks. Okay, so still a product rule right here, right? In between x and e to the x. Bam. Well, you know what? I guess I'm going to make you guys do it. So, can you guys take the derivative? And when you get to the answer, just raise your hand if you get to the answer. Not the derivative answer, just the answer.
Did we ever take the reciprocal? Or no, we don't have to.
We don't have to, yeah, because we don't, let's see.
Oh, we just.
No, because we don't do quotient rule here, right? It's, yep, that's where things get mixed up. You guys are taking individual derivatives of the top and an individual derivative of the bottom.
Like for the product, perhaps. Put them over each other. You just subtract.
Say again, Carson.
Like for the products, you have to like make one of them. You have to like put them as.
Oh yeah, no, just regular product rule. Yep. Regular old product rule. And well, yeah, work with the person next to you. It'd be kind of good just to sort of see if you guys can get the derivative by yourself. There's one product rule inside there. The rest kind of easy there. But try it, and kind of work with the person next to you. Show what you got. Let them show what they got, and kind of work through it.
You just become idiots. As one, then you have to show me you start. She went sleeping. The F, she went back. You the next 26. Yeah. Technically, you have to do really X.
Let me try. Or no, I'll give you guys a few more seconds here. Anybody want to do some shout outs of final answers? Not yet, okay. What do we do? Oh, no moment. Okay.
Did you do the chain rule for the polygon?
You don't have to now that I multiplied the x into it. If you left them like this, let's see. No, still no chain rule because there's nothing. If this was like a 2x, then yes, then you would have to do a chain rule because now you have a function inside another function. One thing you have here is an x function multiplying an e to the x function. All right, I'm going to start it here. And please help me out here. So let's see. Derivative of e to the x. E to the x. Derivative of -1. And derivative of negative x. -1. Boom, done there. Okay, product rule happening right here. So go over here. F times g derivative, bless you, is, anybody write down from the book? F g prime plus gf prime. Now, why did I write it backwards? I don't know. Okay, but let's go with it here. So this guy, this is my f function. This is my g function. And we go ourselves with f function stays the derivative of the g function. It is itself. Ooh, I don't like the way that looks. This is x. The f function comes down, no derivative taken whatsoever. And then the derivative e to the x, which is just e to the x anyways. Plus sign comes down. Then we have ourselves the next one, which is the g function multiplied by the derivative of the x function, which is just 1. Is that right? And then that one is just going to be -1 and the derivative of minus x. Okay, are we good there? Yes. Okay, cleaning it up just a little bit here. That goes away. Let me see if I can squeeze it in right into here. So limit as x goes to 0 from the positive side is e to the x -1. This is x, e to the x plus e to the x -1. There's what I got on the bottom there. And the question is now, can I plug it in? Will it cause a 0 on the bottom if I plug in this stuff? Let's see, it'll cause, let's see, 0 plug it into there. 0 plug it into there. It'll cause a 0. Okay, let's do this here real quick here. So 0 plugged into here, right? That'll make 1, right?
Yeah.
And that's 1 minus 1 is 0. So the whole thing here is 0. Okay, how about over here? Plug in a 0 into here. That's a 1, but then that's a 0. So that becomes a 0. That's 0. That becomes a 1, but I got a 1 minus 1. Not fun. Okay. How do we get this dilemma? We took Pital's rule, but it's still a problem.
Is it because we didn't, they were fractions to begin with and we didn't do.
No, we're good. We're still good there. So I got a question for you guys. Does this fulfill a L'Hopital rule or not? It's an indeterminate form, isn't it? 0 over 0?
Yeah.
Should we take a derivative?
Yeah.
Yes, so you can take the derivative another time if need be.
Is this called the second?
Second derivative of the function itself, but we just take the derivative again.
Okay.
Yeah. So yes, you could take a second derivative, or you can take a derivative again because it just fulfilled L'Hopital's rule right over here. Are we good? Tricky, just a little tricky here. All right, derivative e to the x -1.
Yeah.
E to the x. Okay. Oh, the fun one now. So, if I got this correct, let me.
1 times.
Yeah, it's what it is last time again, and then another e to the x, right? So we got x. I'm running out of room. E to the x plus e to the x. Is that right? That's my product rule. Everybody okay there?
So
Then the derivative of e to the x is e to the x. The derivative of -1 is 0. No, you cannot, because they're not subtracting. They are.
You can make it into.
Oh, you know what? Let's see. You could technically cross out.
yeah.
You can factor them out. I guess you can. Yeah, I have them in there, but let's see. You guys take them out. I'll leave them in there. Let's see what happens. Okay, so I'm going to rewrite it here as. Sorry, guys. Are we good there? I'm kind of writing chicken scratch towards the end over here. Cool. All right, Adrian, did you take out e to the x?
Mhm.
Sweet. Okay, I'm not going to take it out. Let's see if we get to the same answer. Because math is awesome like that. E to the x is on top. I got myself on the bottom. I got myself, let's see, x, e to the x plus 2 e to the x's. Is that right?
Yeah.
Okay, when I plug in my 0 into here, on top, I get myself a 1. Are we good? Plug in a 0 into that. That becomes 0 here. But that becomes a 1 times 2. I got myself a 1/2. Cool. Okay, so then if you did take out the 0, I'm going to go like this, doing it a different way. 0. So hopefully, let's see, I think Aiden did this here. You factored out an e to the x out of all and the whole entire bottom. And you're left with x plus 1 or x plus 2? X plus 2. There it is. E to the x's are gone because they get canceled. Limit as x goes to that over 1 over x plus 2. Plug in a 0 in for the x because that's the only one left, and we get ourselves a 1/2 anyways. Cool. Okay. Product, good. Difference, good. Power. So let's see what we can do with powers. Now, only thing I want to say is on the homework, it just may not, one of them or two of them may not fit the L'Hopital's rules or any of the extensions. And then you just say, does not fit L'Hopital's rule. Ha ha ha. You can put ha ha. Okay. But you don't have time to do any of them that does not fit. Should we do one that does not fit just in case? Sure. Okay, what are we on? C. Just super. Whoa, my pin's not pinning. Oh, that's right. That's why. Okay. Let's do this one. This will be at least quick as can be here. X squared minus 1 over x minus 1. There it is. Goes off to infinity. Awesome. Tell me what the form looks like. Dun, 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 dun. We'll have about 10 minutes for the power. All right. Plug in infinity into the bottom here. That's infinity minus 1. Who cares? That's infinity. 1 over infinity is 0. So here's the form, right? And then we got ourselves this one right here. You could say no at this point already, is that right? But you got 0 over here, minus infinity is 0, 0. Is this a L'Hopital rule form? No, it is not. The difference is only infinity minus infinity, right? Not 0 minus 0.
You get a 0 over 0 and that was L'Hopital.
Uh-huh. Yeah, so this does not fit the form. We cannot go any further with L'Hopital. Okay, we're good. D. I told you it was coming. All right, let's see. Cosecant. Just love trick functions here. Cosecant of x to the x power. That's crazy. Now, think about what in the world does the cosecant function look like? It is the reciprocal of reciprocal of sine. Now, we normally graph cosecant functions based upon the sine function. Is that right?
1 over 0.
Perfecto. So the sine function goes like this, like that. Let's see, what does the cosecant function do? It touches at 1 and positive 1 right here. Boom, boom, right? And anytime you have a sine going to 0, then cosecant goes to infinity. So there's an infinity 1. There is an infinity. There's going to be infinity right here. There's a break right here. Okay, we good there? So cosecant function does this. Cosecant function does this, touches at 1, goes back up here, because there's that 1 there. We're going to go up to 1, turn back around. So what is the limit as x goes to 0 from the positive side of cosecant of x? Infinity. Okay, and then as x goes to 0 from the positive side, where does x go?
Zero.
0, absolutely. So this is infinity to the 0 form. Is that one of the forms?
Yeah.
Yeah.
Equals 1.
It is the power rule number 2, is that right? See, power rule. Trying to find it. Nope, not gonna find it. Okay. Everybody okay though? That's power rule number 2. Sweet. Okay. Now, tricky part here. Ready? And we got just enough time to do this here. Let's jam with it here. So we're gonna do this. We're gonna say y equals, because this is log functions now. We have this x here that's stuck in the exponent. That's our problem. Am I good? So we're gonna say y equals, just as some algebra stuff. Cosecant of x to the x is equal to that. Therefore, ln of y will equal ln of all this good stuff here. Man, a log function and a trig function and a power function? That's crazy. But what happens here is this x gets to go out in front. And because of the rules for logs, we are awesome. We have now got rid of the exponent problem. Okay, and you should kind of tell, like, you know what, that's interesting. If you wanted to. This right here, if you want to actually see the form of this form is a product form, is now, right? And if you checked it out, graph this, you'll see that this goes to 0 and that goes to infinity. But we're just doing the algebra behind it right now. We're good? I got to make this guy into a ratio. Now that's getting crazy. So here's what we're going to do. The trick is I'm going to take this x right over here. And I'm going to make this guy go. Let's leave the ln because that's so complicated. Let's leave the ln and the cosecant of x. Let's just leave that alone. But if I take this down to the bottom, if I take this x down to the bottom, it's going to have to be 1 over x. Or you can do like this. You can say this x taken to the bottom. I know this from algebra. I do this, don't I? Don't I flip this exponent on my sign of my exponent? Exponent of my sign. That's funny. Okay, so then this could be ln of cosecant of x over 1 over x. Okay, we're good there. Bam, and if we think about it, this is going to go to infinity, and that will go to infinity. That is a L'Hopital rule. So let's go. Let's bring in the limit back into this situation. Limit as x goes to 0, positive 0 from the positive side of ln of cosecant of x over 1 over x. Can you take the derivative? And you can check it. It is going to be infinity over infinity as the form.
So just because it's a form doesn't mean enough for L'Hopital's rule?
Say again?
Just because it's a form doesn't mean it'll fit L'Hopital's rule?
Oh, no, if it fits the form, it fits L'Hopital's rule.
And
Yeah.
then we have to do all of the other stuff.
Oh, yeah.
This form, it's you.
Oh, we had to do this form because we are stuck with this guy here in the exponent.
No, just don't work.
We can't take a derivative with x in the base and x in the exponent. Just get stuck. That's when we learn logarithmic differentiation process. Make it.
Ln on the y.
Oh, we'll come back to it. Yeah, we'll come back to it in just a second. We're just trying to deal with it. Good question. Okay, can we go from here? Let's see. Can we go from here? The derivative. Oh boy. The limit as x goes to 0 from the right with 4.5 minutes left. Let's see how we can do this. This is going to be, let's see, the derivative ln is 1 over whatever is on the bottom, right? Or whatever is here, right? It's, you just take this, you stick it down to the bottom. And then what you do is you take the derivative of cosecant of x. What is the derivative of cosecant of x?
Negative cosecant of x cotangent.
Thank you. Negative cosecant of x cotangent x. Okay, on the bottom, 1 over x. What's the derivative of 1 over x? That is something we should kind of just have memorized at this point. It is going to be negative 1 over x squared. So we did that all the way in chapter 3. Done this a few times here, but at this point you should just probably like, yeah, if I have 1 over x, it's negative 1 over x squared. Okay, let's simplify as we go here. Let's see, limit as x goes to 0 on the right-hand side. Oh, I like this. Cosecants are gone, is that right? Boom, boom. I have myself a negative cotangent of x That's where I'm sitting at right there. And I got myself oh man, -1. Okay, so negatives are gone. Is that true?
Yeah.
So I'm getting closer here. I'm getting there. Let's see what else I'm getting here. Oh, you know what? Let's see. I have a complex fraction in my hands, right? So I can make this. Can I take the x squared, take it to the top? Is that okay? Is that okay? Just want to make sure. This is going to be to the top now. This is going to be x squared cotangent of x. Is that true? Just making sure we're good there with the algebra stuff behind, because algebra is the tedious part here.
Is it not something new?
Negatives canceled because we had negatives on top and bottom. All right, and this one, we look at this one and says, you know what? Actually, we have ourselves the same problem. That goes to 0 and that goes to infinity. That's a product rule. Let's change it to let's see, the way I want to change it most likely would be leave the x squared on top, but change this to a tangent x. Not taxes, that's on my mind, but tangent x. Okay, and then does this fulfill L'Hopital's rule? Yeah, 0 on top, 0 on the bottom. We take a derivative, limit as x goes to 0 from the positive side, we get ourselves 2x over secant squared. Is that right? And then we plug in the 0. 0, that would be a 1, that would be a 0, so that becomes a 0, and we're not done.
Oh,
Because this is not the limit of the starting point. This was
line of y.
of ln of y. It's almost there, and 35 seconds to go. So 0 is ln of y. So let's go back to our original inequality that we made. So this one now gave us this. Is that okay?
1.
So then what we do is we have to put in a base of that. Those guys get canceled. Y is equal to e to the 0, which really is just, we good? Because remember, y was our original function in the beginning, right? Y is what we did. So yeah, you have to add in the little e back into it. Okay, guys, was that helpful?
Yes.
Okay, I'll let you guys try the homework at this point, and then come back and we'll do 4.5 on Wednesday. Finish up. I think that finishes up chapter 4, but I'll check. Oh no, like 4.7 I think is left.
Now, Danny has the next one. Oh, is there? So, I'm actually. Wow. Very long.
So,
You are